let me just share my screen. Okay, so can you guys see my screen now?
Yes, sir.
Alright, so for today, we'll try to finish two modules again since they are just a short discussion. So we'll try to finish the module 9 and then the module 10, okay, which is the Delta-Wye and Wye-Delta. So let's start with module 9 first, which is the source transformation. So to give you guys a brief idea, okay, so when we say source transformation, so we only have two sources, right? So it could be from voltage to current or from current to voltage. Okay, so either of those two. Okay, so we have additional wherein a voltage which is dependent to current. Okay, and then a current which is dependent to voltage. So we have some cases like that. But anyway, as long as you know the basics of this one voltage going to current, you will know later on how to deal with dependent voltage. Okay, so for this one, of course, we call this one independent voltage going to independent current. Okay, and then independent current going to independent voltage. All right. So another trivia is if we are going to transform voltage to current, okay, I'll just put it right here. If we're going to transform voltage to current, okay, so what you need to apply is, okay, I'll just put it down right here. So initially, before you can transform a voltage into current, it must be in a series connection, okay? Series connection. So what are those connections that I'm talking about? So of course, when it comes to voltage, before you can transform that one into current, you need a voltage and then a resistance because I is equal to V divided by R. Okay, so this voltage and resistance must be in series with each other. Okay, voltage and resistance, okay, must be in series with each other. Okay, and once that one is, okay, like it met the condition, they are in series, then you can now transform that one into parallel connection. Okay, so it's now the opposite. So instead of having a uh, series voltage and resistance, we will now have a parallel connection of, so V, we are now into current, wait a second, voltage, and then resistance going to current. And then we now have a current, yeah, current and resistance. I is equal to VR, V is equal to IR. Yeah, current and resistance. So it is now the current and resistance which are in parallel with each other. Okay, so if you're confused for now, so let's just have this shorter description. So voltage to current, so it is going from series to parallel. Okay. So just get this idea for now, and then later on let's talk about the components under series and then the components under parallel. But yeah, that is the idea on how to convert a voltage to current. So it should be from series going to parallel. And then for the current to voltage, so it's the opposite. So just get this one. So it is now in parallel to series. And for this one, so initially it's in parallel, okay, and then it will go to series connection, okay, so something like that. So again, this is the one that you should look first before you can transform this current into a voltage. Okay, are they in a parallel connection, this current and resistance? If yes, then you can now transform that one into a series connection, which is now in voltage and resistance series connection. All right. So let me remove this one to avoid confusion. Oops. Well, anyway, so I hope you guys get the idea on how to convert voltage to current. Okay, so basically this is already your foundation on how you will convert um, sources. All right. Okay, so without a further delay, let's now start with the background study. So, uh, source transformation is an electrical network can consist of sources and passive elements. So sources are circuit components which possess their own energy and are capable of transferring this energy to other circuit elements. Okay, so you already know that one. So the components that can transfer energy is a source. It could be a voltage or it could be a current. Okay, so there are two basic types, like what I've said a while ago, a voltage and then a current source. So again, it could be independent, just like what we have in here, which is independent. And we also have dependent sources, wherein they depend on the other components. Okay, so in the case of independent sources, it's very straightforward. The voltage or current is fixed. So whatever is the value of that, that's the final value of that voltage or current. However, independent, so this might vary. Okay, like for example, initially you have 5 volts, but this one is depending on the current. So if the current changes, your voltage right here will change also. Okay, because this one could be 1 amp, this one could be 2 amp, this one could be 3 amp. So depending on your computation with this current right here. Okay, so the same with the current source. So if we have initially, let's say 5 amps, and then this one is depending on the voltage. Okay, so if we have higher voltage, then this will change also the value of 5 amps right here. Okay, or vice versa. If this is lower, then this will make this one lower. All right. So yeah, and then for the passive components, so we already know that one. So for the passive components, we have resistors, capacitors, and then inductors. So whatever is the value of that component, that's it already. Okay, we cannot do anything about it anymore because it's a fixed uh, component. Okay, so we call that one passive components. All right. So in analyzing electrical networks, okay, so we can have a very simple, okay, let's say voltage divider into a very complicated circuit like internal structure of an integrated circuit or IC. Okay, so initially, of course, you can dissect that one into smaller chunks. Like in this IC, we can have, let's say, 10 parts. Okay, so let's have a paint. All right, so let's have some shapes. So let's say this is your IC. And then, of course, this IC has a lot of parts. Like, for example, let's say this is your voltage component. This is your microchip, wherein this restores the program and or etc. etc. This is the reset button. This is the let's say mm, let's have a processor with this microchip. Okay, and then we have RAM that deals with memory, etc. etc. So this is just an example. Okay, so of course you can deal with this one first. Okay, deal with this one first and then dissect that one into maybe two or three if you can still do it. And then of course you can convert this one into a different circuit. Okay, wherein let's say initially this one has a voltage source, wherein you can convert this one into a current source. So that is also possible. Okay, so the good thing in transforming a voltage into a current source, so whatever is the functionality of this one, it's still the same. It just required a different source. So before it's voltage, but right now it's now requiring a current source. Okay, but for the others, so there might be some components that cannot be dissect anymore. Like whatever is their structure, it is already the fixed structure. Okay, but yeah. Anyway, that's the idea. Okay, on solving a simple into a complicated circuit. Okay. All right. So here's a list of important theorems along with a brief explanation. So we have already discussed superposition. So when we see superposition, we can is this? Wait, let me just recall. Yeah. So this is very good if you have multiple sources, and then Thevenin's theorem and then Norton's theorem. So this is also good if you want to get a simplified version of that circuit. Like for example, in Thevenin's, of course, you will have a single voltage source, okay, and then a single resistor. And then for the Norton's, then this one now is a single current source. And then of course a single resistor also. Wait a second, guys. Kulit. All right, and then for the Millman's theorem, so we haven't discussed this one yet. So maybe next meeting or next week. So this one is a simplification technique involving circuits with parallel branches. Okay, so at this point, it should be noted that all these theorems are based on the basic rules governing the field of electronics. So namely, Ohm's law and Kirchhoff's laws. Okay, so basically you can apply Ohm's law and Kirchhoff's law on those theorem. Okay, but mostly Ohm's law will be fine. Okay, because Kirchhoff's law is like another uh, idea or different theorem, but this one is still helpful, especially the KCL and then the KVL. Okay, so in addition, in which we are going to discuss this one later on, which is the delta to y configuration or y to delta. So sometimes they also call this one a star to delta or delta to star. So either of those two. So those two namings are just the same. Okay. All right. So here's now the topic for the source transformation for independent sources. So take note, the one that we're dealing for now is independent sources. So consider the circuit shown in figure 1, which is this one. So the goal is to find the current denoted by I. So our goal right here is to find the current that is flowing on this 5 ohms resistor. Okay, so how do we do that one? Here, mesh analysis, Kirchhoff's voltage law or KVL cannot be applied readily because the circuit has a branch which has a current source. Okay, so if we don't have this one, we only have a voltage source right here, then just by applying Ohm's law or KVL or KCL, we can already solve for this I right here. Okay, but since we have a current source right here, we cannot do that one directly. Okay, so in here, since we have a current source, we can convert this one into a voltage source. Okay, just by applying source transformation. So thus, we need to devise a method by which we can eliminate this current source from our circuit. Okay, so how do we eliminate this one? Just by transforming this one into a voltage source. Okay, all right. So in here, let's have our example for now before checking if we have the correct result. You already have a paint? Yeah. All right. So our goal for now is to convert this current source into a voltage source. So if we are going to check the requirements, so current going to voltage, it must be in parallel first before you can make it into a series connection. So again, check. So if it's parallel, then check if it's the current component and then the resistance component. So if yes, then you can now proceed into transforming this one into a series voltage and resistance connection. Okay, so how do we do that one? So as you guys can see, we have met the condition wherein they are in parallel with each other, which is the current and then the resistance. Sorry for that. Masyadong malikot yung pusa namin. Alright. So right here, just apply Ohm's law. Okay, so we need voltage, right? So just recall the formula. Ohm's law, V is equal to I times R. Okay, so in here our I is 1 amp, 1 amp times the resistance 10 ohms. So we will get a voltage source of 10 volts. Okay, so in here, if we are going to transform this one into a voltage source, so let me just get this one, and let me delete this one, and delete this one, delete this one, delete that part. Okay, so in here we are going to put the voltage source right here, and then the resistance. Okay, so take note, if you're going to transform a current into a voltage, the resistance component on it, so it could be in parallel or series, will stay the same. Okay, so in here we have 10 ohm resistance, so it will stay as it is. Okay, so the value of that one will not change. But for this one, so from current, it will now become a voltage source, which is a 10 volt source. Okay. And then one thing that you should also take note is the flow of the current. So wherever is the arrow pointing, that is the positive, uh, call this one positive polarity. And then the tail of that one is of course negative. So that is why we have positive right here and then negative right here. Okay. So are we clear so far for our first example? Did you guys get the idea? Or are you guys confused? Hello? You guys still there? Alright. So, medyo sir, clear po. So, maybe Mr. Augustine also got this one. Alright. So, again, just take a screenshot of this one and then, yeah, this is all you need. Okay, in transforming a voltage to current and then a current to voltage. Alright. So in this example, we've met those conditions. So we now have this voltage transformation from a current. Okay. So let's have more example. So let's see. All right. So there you go. So for the step one, we've got it correctly. So we now have 10 volts right here and then the 10 ohm resistor. Okay. So it will stay as it is. But we haven't figured out yet on, how to get the current right here. Okay. So in here, the process to get it out here is called source transformation. We have transforming this current with a parallel resistor, voltage source with a series resistor. All right. So in here, we can actually simplify this one now. Okay. But if you want, you can actually already apply. Okay. We can actually already apply KVL right here. So KVL on this part and then KVL on this part, and then apply the simultaneous equation. Okay. But that one now is like more on the formula of a Kirchhoff's law. It's not like applying source transformation anymore. Okay, so that is why we will not apply that one for now. Okay, so what we will do is we will simplify this one using Ohm's law and then convert this one into again using source transformation and then apply Ohm's law and then source transformation until we will get or until we will arrive into a series connection. Okay, because once we have a series connection, whatever is the current that is flowing in here is now the same with the current that is flowing in here. So with that, we'll be easily know the current of this node right here. Okay, so for now, let's transform this one into a simpler circuit by combining this resistance right here. So as you guys can see, this 10 ohm resistance and 5 ohm resistance is in a series connection, so we can add them. So 10 plus 5 is 15. Okay, and then this 10 volts right here will stay as it is. Okay, so once you're done in combining them, you will have this circuit connection right here. Okay, so again, we can apply mesh analysis already, or uh, KVL or KCL. However, there is also much easier graphical way of achieving this one. Or we will just simply apply source transformation, because that is the topic for today. Okay? Because what is the point of having this module if we will apply another uh, theorem? Okay? So we will just simply apply source transformation on this example. Okay, so once you have combined those two, we can actually put the 5 ohms right here on the left side, and then the 10 volts right here on the right side. So you can now have this connection right here. And as you guys can see, okay, so this voltage source right here is actually convertible into a current source. Okay, the same with this one. Okay, so again, let's go back with our notepad. So if we wanted to convert a voltage into a current, okay, voltage into a current, so it must be in series first, going to parallel. And then take note, we have to see if the components that is in series is correct or no. So check if there is a voltage. So yes, there is a voltage. And then check if there is a resistance. So yes, there is also a resistance. Then you can now perform this connection right here. Okay, so just apply Ohm's law. I is equal to V divided by R. So if we are going to get this one, all right. So let's transform this left side branch right here. So if you're going to get the current source of this one, so I is equal to V divided by R. Okay, so voltage is 10 volts. Okay, and then R is 5 ohms. So we will get 2 amps right here. Okay, and then if you're going to transform this one into a current source, so let me just delete this one and delete this one also. All right, so in here, the current will stay right here, and then the resistance will be placed in here. Okay, so current is 2 amps, and then the resistance value will stay the same, so 5 ohms right here. All right, so that's how we convert the left side branch. And then take note, wherever is the positive side, that is actually our arrow. Okay, and then the negative is the tail of that arrow. All right, so there you go. So are we clear so far? Hmm? Aray, aray, aray. So did you guys get the idea on how to convert a voltage into a current? Okay, how about the others? I hope you guys got the idea also. So this is just actually, purely Ohm's law. All right. So if you know Ohm's law, and then you know the idea on how to convert a voltage to current and then current to voltage, then you're good to go. Okay. All right. So just wait a second, guys. 1 minute. All right. So sorry for that one. So let's now solve the right side branch. So the same concept. So as you guys can see, we have a series connection of a voltage and then a resistance. Then if that condition is met, then we can now transform this one into a current source. So I is equal to V divided by R. So voltage is 10 volts and then resistance is 15 ohms. Okay, so this is equal to, where is my calculator? 2/3 or 0.66667 or 0.67. Okay, amps. Okay, so if you're going to draw this one, so again, take note on the polarity. So going up, and then right here will be the resistance, which is still 15 ohms. Okay, so masyado yata mataba. Right, so there you go. So 2 amps, 5 ohms, 15 amps, and then 0.67 amps. Okay, so are we clear so far on the right side equation? Did you guys got this one or no? All right. So what about the others? Only you, Miss Maxine. All right. So in here, we have another thing that we can do to simplify this one further. So as you guys can see, we have the same. I mean not the same. So we have parallel connection of current, and then they have the same polarity. So we can actually add those two currents into one. Okay, arriving into one current and then into three resistance. But we can actually combine those three resistance into a single resistance. But before that, let's see what is the next thing that we'll do here on the step number two. So for this step number two, we are already done with this one. So we have already converted the uh, this voltage source right here into the current source, which is this one. The same with this one into a current source. So in here, we can actually add those two. So the circuit in figure 4 has two current sources pointing in the same direction. Okay, and hence this can be replaced by a single current source whose value is equal to their sum. Okay, so that is why if we are going to add those two, 2 amps plus 2/3 amps, it will give us a value of 8/3 amps. Okay, I see. Well, anyway, since this one is recorded, so you can just rewatch this one again, Miss Jade Ventura. Okay. Well, anyway, so once we're done in adding those two, we will have this kind of circuit right here. Okay, 8/3 amps. Okay, for the single current source. Okay. And then for the 5 ohms and then 15 ohms, we can actually combine those two also, wherein they are in parallel connection. So just apply this formula right here. So 5 times 15 divided by 5 plus 15, you will get 15 over 4 ohms. Okay. And then in here, you can again apply another parallel connection for the resistance of 15 over 4 and then 5 ohms. And then we can now have a single series connection. Okay, just like this one. Okay, whoops. My bad. Okay, so well, I think you can also do that one, and then we can now get the current. But in here, we've just applied. Okay, we just applied again another source transformation. Okay, wherein this current source right here became a voltage source, and then of course from parallel it now became a series connection. Okay, so again to do this one, Okay, so let's get, how many minutes do we have more? So in here, if we wanted to convert this current into a voltage source, then we need the current, which is 8 third times 15 over 4. Okay, so if you're going to use our calculator, 8 times 15 divided by 3 times 4. So we will get 10 volts right here. Okay, which is now the same with this one. So 10 volts, and then the value of resistance will stay the same. However, it will now be transformed into a series connection like this one. Okay, and then from here you can apply any method that you know. So in here we've just applied KVL to find the current that is flowing in here, which is 8 over 7 amps. Okay, or you can just apply Ohm's law. You can combine those two, and then you can get the total current that is flowing here, which is still the same, 8 over 7 ampere. All right, so that's it for now, and we will just continue the rest on the part 2. So goodbye for now, and